time moves slower on Mercury than it does on Earth. A day on Mercury is 58 days, 15 hours and 30 minutes on Earth. We can tell this by observing Mercury through telescopes and timing how long it would take for Mercury to complete one full orbit around the Sun. However, if we traveled to Mercury and started our timer there, we would not get the same figure. This is because time does not move as constantly as you might think. It can be affected by speed. The faster you go, the slower time goes for you. But it can also be affected by gravity. And Mercury is much closer to a massive source of gravity in our solar system, the Sun. But how much does gravity affect time? Could we live to incredible ages if we all went to live on Mercury? I'm McColgan and you're watching Astrum. Join with me today as we answer this question and explore the strange and warping world of general relativity and gravitational time dilation. I hope by the end of this video to have earned your like and subscription. To begin with, what exactly is time? Mark Twain once said that time is what keeps everything from happening all at once. It separates yesterday's events from today's and today's from tomorrow's. As you sit here and watch this video, you are not doing what you were doing yesterday or tomorrow. You are watching this video. You are constantly traveling through time in the direction of the future at the rate of 1 second per second. This is the normal speed for traveling through time and is shared by you and everyone else on the planet. But this speed doesn't have to be the case. As discovered by Albert Einstein, the faster we travel through space, the slower our time becomes, up until the point where if we somehow could travel at the speed of light, time would stop moving for us. If we were to travel to an object 4 light years away from us, to people here on Earth it would look like it took us 4 years. To us, it would look like we arrived at our destination instantaneously. Although this sounds incredible, scientists have proven that this actually happens. They took 2 clocks. One they put on a plane and flew around the world with it on board, increasing its speed for an extended amount of time, while leaving the other at a stationary location. When they eventually returned and compared the clocks again, they found that the clock that had traveled faster had actually recorded less time, in line with what general relativity had predicted. General relativity is a real thing. But Einstein also predicted that this would happen with gravity. The closer you are to a large source of gravity, and the more mass that source of gravity has, the slower time will go for you. This was proven to be correct in 1959 with the Pound-Rebka experiment, where they shot gamma rays from the top of a tall building to the bottom and recorded whether anything had happened to the light waves. They found that the frequency of the waves increased the closer to the Earth they were. Kind of like cars bunching up in congested traffic, the peaks of radiation moved closer together. Time slowed down ever so slightly for the gamma radiation the closer it got to the Earth. This effect is significant enough that satellites have to be programmed to account for it, because when they are further away from the Earth's gravity, time moves more quickly for them. Without this correction, their internal clocks would go out of sync with our clocks on Earth, which would cause problems. And yes, that's right, the Earth's gravity is enough to cause time to slow down for us. So you're probably now thinking, how much faster would time be going for me if I wasn't on Earth or if Earth had no gravity? Well, it's a matter of perspective. The precession of time will always appear the same from your perspective. You won't feel like you're going slower, although you may notice some weird stuff going on around you. But it's the outside observer that has to deal with you slowing down. To find out an exact answer to the question, Einstein devised the following equation. We will be using this equation a lot in the rest of the video, so let's try to understand it. It looks a little scary, but it's not as bad as it looks. T0 is the answer we're looking for, how much time would pass on the object we're interested in this case the Earth. TF is how much time would pass in a place completely unaffected by gravity. Such a place doesn't exist, by the way, but it is our hypothetical stationary clock. G is the gravitational constant, a number they added to basically make the sums work out. we're not going to worry about where it came from. All we're interested in is the fact it's always this. And don't worry too much about that metric at the end. M is mass, specifically the mass of the object creating the gravity. R is the distance from the center of the object, and C is the speed of light, a figure we know to be roughly 300 million meters per second. So to find out how much slower time goes on Earth compared to somewhere where there was no gravity, all we have to know is how much mass the Earth has, how far we are from its center, and then we can decide how much time we want to compare. Just to ease ourselves in, I decided to try this formula out with 60 seconds. If 60 seconds passes in our place unaffected by gravity, how much time passes on Earth? I plugged in the information and got our result. For every 60 seconds that passes, people on Earth experience only 59.9999996 seconds. In other words, 6 billion seconds have to go by before we notice a difference of 4 seconds. This happens roughly once every 190 years. So realistically, you'll only gain about 2 seconds over the course of your entire lifetime because of the Earth's gravity compared to a place with no gravity. This is a little underwhelming. However, we here on Earth are not just affected by our planet's gravity, we are also affected by the gravity of the Sun, which in terms of our equation is much more significant. So let's try this again by inputting the mass of the Sun and our distance from it into the equation. This gives us the new figure. How much time goes by for us on Earth for every 60 seconds of actual time that goes by? 59.9999994 seconds. While this is a more significant number, it does mean that you are only seeing a difference of a second once every 3 years or so. Or in other words, about 24 seconds over the course of an average human lifetime. But Mercury is much closer to the Sun. Surely time is significantly altered here compared to Earth with a massive object like the Sun so close by. How much more does time slow down for us on Mercury? The equation is essentially the same as before. The only new number we need is the distance between the Sun and Mercury. The answer to our final question of how much time passes on Mercury every 60 seconds is 59.99999 seconds. 60 million seconds need to go by before there's a single second's difference. This happens roughly once every 1.9 years, which scaled up across a lifetime equates to about 38 seconds difference. Only 14 more seconds than Earth. But from your point of view, you're not really gaining those seconds, because from your perspective, time would be moving normally. It would be the Earth that is moving ever so slightly faster from your point of view. So if you pointed a telescope towards Earth, you'd see 14 more seconds of Earth in history than you would if you were living there. As Mercury is fairly inhospitable, this probably isn't worth it. So, does Mercury's proximity to the Sun allow time to move slower for you compared to Earth? Yes, but only by a difference of about 14 seconds over your entire lifetime. In reality, time dilation due to gravity is not actually that significant, at least not in our own solar system. The mass of the Sun is not enough to really stretch time that much for us, even if we were as close to it as Mercury. The Sun would need to be millions of times more massive before we would begin to experience time dilation to any significant degree. However, it's still a fascinating insight into the way that time flows in our universe, and reveals that time is not as constant as we might think. And of course, it begs one final question. Are there any objects in the universe that are massive enough that we'd experience significant time dilation around them? There are. And this is where things start to get very noticeable to an outside observer. At the center of galaxies exist objects known as supermassive black holes. These objects have masses that are millions to billions of times the mass of our Sun. In other words, if you were to fall towards them, time could slow down for you so much that it would approach zero. If you were to get close enough to one of these giants and later escape it, you could spend half an hour around there and emerged to find that hundreds of years had passed to the people back on Earth. People on Earth with a powerful enough telescope would see you barely move. Even your breaths would take days to complete. In fact, there would be a point right at the edge of such a body that as you approached it, your time would hit zero. What would happen if you passed that point? Our equations break down and so cannot explain what lies beyond that horizon. Science does not yet have the answer, although there are certainly many theories. But that might be better explored in another video. Movement through space is inevitable. You might not feel it, but right now you're sitting on a planet that is spinning on its axis, moving you at up to 1,600 kilometers per hour depending on your latitude. The Earth circles the Sun. The Sun moves through the Milky Way. The Milky Way moves through the local group of galaxies. And the local group moves through our local supercluster. And even that supercluster of galaxies is in motion, heading towards the Shapley supercluster, where scientists believe that there is a particularly large concentration of galaxies. I hope all this motion isn't making you too dizzy. But on the grandest scales of our universe, something strange is happening. Scientists have begun to realize that there is not enough mass in the Shapley supercluster to pull us towards it at the rate that we see. About 50% of the cause of that motion is unaccounted for. In 2017, researchers discovered a possible source for the rest of that motion. But it's not something pulling us, it's something pushing. I'm Alex McColgan and you're watching Astrum. Join with me today as we explore the evidence for the region of space known as the dipole repeller and try to understand how, in a universe filled with gravity, something can push us instead of pull. Let's start with a little context. It's taken a long time for astronomers to recognize that this motion was taking place. To understand that we were moving, scientists first had to make a map of the regions of space around us. And although we as a species have been mapping the stars since the beginnings of civilization, it was only thanks to Mr. Hubble in 1924 that we proved there are actually stars in other galaxies outside the Milky Way. Before then, although astronomers had seen fuzzy little clusters of light in the night sky that we now know to be galaxies, the common wisdom was that these were gas cloud spiral nebulae within the Milky Way, not something that existed beyond it. Hubble noticed several Cepheid stars, a type of variable star with a cycle of variation closely linked to their luminosity, within one such spiral nebula, and used the fact that this luminosity was very predictable based on distance to calculate very precisely how far away they were. Surprising many, he proved that they do exist beyond the Milky Way. Since then, astronomers have been scrambling to catch up with the new reality of galaxies and superclusters, and set about mapping the locations and distances to every galaxy they could find. Hubble had been studying Andromeda, our closest neighbouring major galaxy, but there were others. By the 1970s, Stephen Gregory, Lard Thompson, and William Tift definitively proved that galaxies didn't just float randomly in space, but converged into superclusters, large filamentary or sheet-like structures that exist between large bubbles of void. They mapped the first supercluster, the Coma supercluster, which covered a region of space 100 million light-years across. A whopping 95% of all galaxies are found in these superstructures. It wasn't until 2014 that our own supercluster, the Laniakea supercluster, was fully mapped. You might be surprised to hear it happened in that order. After all, wouldn't common sense say it's easier to map regions of space closer to us rather than ones further away? Why was it only nearly a century after the discovery of other galaxies existing, and 40 years after mapping the first supercluster, that we finally turned to our own? The answer is that mapping the local regions of space around us is surprisingly challenging. And it's all because of the Milky Way getting in the Milky Way. The Milky Way is full of gas and dust, and these regions are so difficult to penetrate that we can't really see beyond them. Towards the center of the Milky Way, this effect gets so bad that scientists have dubbed the whole area the zone of avoidance. Very little light gets through it. Not being able to see in this area is particularly relevant to our current discussion for reasons we'll get to later. In contrast to our local area, distant galaxies are easier to study, as all you have to do is point your telescope at a single point in the night sky and let it drink in the light. Mapping the area around us requires looking at every point in the night sky. It's proved quite difficult, although astronomers are now getting a better handle on it. Thanks to their efforts in looking at thousands of galaxies in our galactic neighborhood, and by studying galaxies' peculiar motion, or their motion relative to the cosmic background radiation that ignores the expansion of the universe, scientists have been able to group gravitationally bound galaxies into superclusters. At the center of our Laniakea supercluster lies a point known as the Great Attractor, an area 150 to 250 million light years away from us, that we, in the Milky Way, are slowly drifting towards. Sadly, the Great Attractor lies within the zone of avoidance, so it's tricky to see clearly what lies there. To confound things further, the Laniakea supercluster was also found to be moving. It travels towards another supercluster known as the Shapley supercluster, taking us along with it. At the center of this supercluster lies the Shapley Attractor, which also is believed to be incredibly dense in terms of mass. But frustratingly, this second attractor also lies in the zone of avoidance, making it difficult to see exactly what's going on over there too. Thankfully, as X-ray and infrared telescopes improved, it became possible to take a better look at these two attractors. But this is where the mystery begins. What mass is there is not quite massive enough to account for our apparent motion in that direction, which is why a team of researchers from the University of Hawaii published an article in Nature to attempt to explain this discrepancy. The team was made up of Yehuda Hoffman, Daniel Homerede, R. Brent Tully, and Helene M. Courtois. Together they created a new kind of map of the local universe around us. This time, instead of simply noting galaxies' positions, they highlighted their motions instead. This allowed them to create a map of flow lines, which, after mathematical analysis, allowed them to make assumptions about the locations of masses in our nearby superclusters. Their results were surprising. A lot of our local mass is moving towards the Shapley supercluster, which is what you would expect. But they also found a lot of mass is moving away from another specific region in space. They call this mystery patch of space the dipole repeller. Together, the dipole repeller and the Shapley attractor both contribute about 50% to our motion, working together in tandem, hence the name dipole. But how? Gravity is a force that, so far as we have observed, only pulls. What lies in this region of space that allows a push to happen? Could it be a strange collection of white holes? The theoretical opposite of black holes that we've talked about in videos before? Or perhaps some source of anti-gravity? Not quite. The answer is nothing. The dipole repeller is a void, a bubble about 100 million light years across that does not contain many, if any, major galaxies. It's one of the bubbles that exists between the filaments of the universe's structures. But interestingly, our galaxy's current motion lines up much more satisfyingly with the push from this region than it does from the pull of the Shapley attractor, which is a compelling argument in this theory's favor. So how does nothing push? The answer is actually that this could be a pseudo-force more than it is a real one. Imagine a universe where all the galaxies were spaced equally. While the gravity of galaxies above would pull you, the gravity of galaxies below you would do the same. So would the pull of galaxies to your left and to your right. In this way, the varying forces of all these gravities would balance each other, leaving you to not really travel in any direction. You'd be in a perfect equilibrium. But what would happen if we removed the galaxies from one of these directions? What would happen if we added a void? Well, then the scales would tip. There would be one direction that no longer pulled you, leaving the opposite direction's pull to act on you unimpeded. As a result, you would move away from the void as if it were pushing you. Everything near a void will thus move away from it, making it seem to have a repelling gravitational force. It is something of an optical illusion. There is another explanation for why a void space might push you, which might work in tandem with the pseudo-force. The universe is expanding, and that expansion shows no sign of slowing down. In fact, it seems to be speeding up. However, this expansion is counteracted by gravity, and in areas where there is more gravity, less expansion seems to take place. Stars aren't just being pushed away from each other, they're also being pulled together. Conversely, in a void, there is nothing to contain this rampant expansion. As a result, void spaces literally will swell compared to their supercluster counterparts. It might be done by warping the fabric of reality, but this also achieves a sort of push. Since 2017, not much more has come to light about the existence of the dipole repeller. As this is still an expanding field of research, there's some debate about whether it's really there, or how influential it might be on our galaxy's current motion. It is difficult to observe due to the Milky Way's obscuring effect, and there is always a challenge inherent in trying to spot the absence of a thing rather than its presence. However, Tully and his fellow researchers hope that with the aid of future ultra-sensitive surveys in multiple spectrums of light, it will be possible to map out the few galaxies that lie in this void, and generally confirm its existence in the region they hypothesize. We are constantly moving through space, but even the science of space is always in motion. Each new galaxy, along with data regarding its redshift and travel speed, helps us develop a broader understanding of the movement of the galaxy. It's fascinating to think that not all of that motion is caused by the pull of gravity. It might turn out that sometimes the universe just needs a little push to get going. Tune into the universe with the right equipment and you will hear it humming, no matter where you look in the sky. Of course, it's not possible for sound to travel in the vacuum of space. Instead, we are talking about the hum of gravitational waves. You might already be familiar with a similar signal discovered decades ago. It's called the cosmic microwave background, and it is the afterglow of the Big Bang. This glow of microwave light was a groundbreaking discovery. It was the smoking gun that solidified the Big Bang's place as the leading theory of our universe's beginning. Yet, this light signal had a glaring weakness. Despite it being the earliest light of our universe, it was emitted almost 400,000 years after the Big Bang. If we want to go back earlier, we will need a background signal made not of light, but of the ripples of the fabric of space-time. In 2023, astronomers at the NANOGrav collaboration have announced that, by using a clever trick, they may have detected just that. Using exotic stars as a galactic-sized gravitational wave detector, they measured the faint hum of space-time itself. This hum of gravitational waves might just be the reverberations of the very creation of our universe. I'm Alex McColgan and you're watching Astrum. Join me today as we learn about the secrets of gargantuan gravitational waves and the ingenious new method astronomers have used to detect them. In a previous episode, we covered the LIGO detector and how it uses lasers to precisely measure the minuscule changes in the length of a tunnel caused by gravitational waves passing through. These gravitational waves stretch and squish space-time, causing changes in the time it takes for light to travel from one end of the tunnel to the other. But detectors like LIGO are only sensitive to a specific kind of gravitational waves. Like light waves and sound waves, gravitational waves can come in different frequencies, and LIGO is only able to listen in to one part of this spectrum, the high frequencies. That's when these binaries are spiraling in on each other rapidly, completing hundreds of rotations per second before colliding in a great bang. But that is also why LIGO cannot listen in on the much earlier stages of these binaries, when the objects are orbiting each other at a much greater distance. Because these orbits are much slower, the gravitational waves they produce are of a lower frequency and energy. So you could say, rather than a great bang, they give off a faint hum, combining into one collective signal. Bigger black holes give greater contributions to this signal. The loudest contributors would consist of pairs of supermassive black holes, the kind you'd find at the center of galaxies. These binaries, which consist of black holes billions of times the mass of our Sun, are expected to be rare because they only form when something truly spectacular happens, the merger of two galaxies. When galaxies merge, because of the vast amounts of empty interstellar space in them, they mostly phase through each other. Very few, if any, actual collisions of stars or planets happen. But the stars gravitationally attract one another and merge into one collective galaxy. And the nuclei of these galaxies, the supermassive black holes, form binaries that continue orbiting one another long after the galaxy merger appears to be complete. It's these remnants of galaxy mergers that we would hear most strongly in the ultra-low frequency range, specifically around the nanohertz range. Yet, just like how the human ear cannot hear sounds with ultra-low frequencies, LIGO is deaf to this cosmic cacophony. If we could listen in, we would gain new insight into galaxy mergers and black holes. But that's not all. One of the most exciting things about the gravitational wave background is that it is a window to the very first moments of our universe's existence. Let's quickly recap what we know about the cosmic microwave background. This microwave light is the earliest light that we can detect because for the first 400,000 years, the universe was opaque to light. What does it mean for the universe to be opaque? Initially, the universe was far too hot for neutral matter to exist. Electrons and protons were unable to bind together and form neutral atoms simply because they had too much energy. This state of matter is called plasma, the same stuff that stars are made of, and the universe was filled with it. Light gets trapped in plasma, unable to move through space without bumping into the charged electrons and protons, being continuously absorbed and emitted. But once the universe expanded and cooled down enough for the protons and electrons to coalesce into neutral hydrogen and helium atoms, it suddenly became transparent. The light was finally freed. This light was then stretched by the expansion of the universe until it redshifted into microwave light. This is why the cosmic microwave background is the earliest light of the universe. But gravitational waves are not made of light. They are made of space-time itself. Plasma is no obstacle to them. To gravitational waves, the universe has been transparent from almost the very instant of the Big Bang itself. They can penetrate past this plasma barrier and offer us a glimpse of the very first moments of the universe's creation. Because these primordial gravitational waves have been traveling for so long, even if they were originally produced with a high frequency, they would be greatly stretched by the expansion of space-time. They would be redshifted into ultra-low frequency gravitational waves, the same kind that would come from black hole binaries. Together, these multiple sources will give us a so-called stochastic gravitational wave background existing over a range of low frequencies. How can astronomers retrieve this treasure trove of information about black holes, the Big Bang, and more? Can we build a better LIGO and detect how the Earth is bobbing up and down in these gargantuan gravitational waves? Well, LIGO works by sending two beams of light being sent along perpendicular tunnel arms. The beams are reflected by mirrors at the ends of each of those tunnels, and they return to the starting point and are compared with each other. This is so that if space-time gets distorted along one direction, the information from the other direction can be used to get a sense of how much it has changed. Unfortunately, if we were to design a new LIGO to detect these gravitational waves, we would need to have tunnel arms that are much larger than anything we could build on Earth. This is because the frequency of a wave is inversely proportional to its wavelength. Ultra-low frequency waves have an ultra-long wavelength, and would require us to look at changes over a much greater distance to notice the effects of these gravitational waves. For nanohertz waves, that is, one full fluctuation taking a billion seconds, a quick calculation, wavelength equals speed of wave over frequency, tells us that the wavelength would be around 10 to the power 17 meters. For a sense of scale, the distance between the Earth and the Sun, or an astronomical unit, is 10 to the power 11 meters. A light year is around 10 to the power 16 meters. The wavelengths we are discussing are tens of light years long. Clearly, we cannot build anything suitable for this task on Earth, or even in the solar system. We need to go beyond our stellar neighborhood. But rather than wait for humanity to ascend beyond the confines of our solar system and become a spacefaring civilization, astronomers at NANOGrav have used a clever trick. You may recall our recent episode on pulsars and how we discussed that these ultra-dense neutron stars are able to spin with remarkable stability. They emit light along their poles, and we can detect the pulses that we receive as those vast beams of light swoop around and hit the Earth again and again. These pulses come with such precise certainty that they are used as clocks of the cosmos, able to keep time across vast distances. Therefore, we can use already identified pulsars to supply us with reliable signals from thousands of light years away. The pulsars are like the mirrors at the end of the LIGO arms, but rather than sending us back a signal we send across, they are generating their own. NANOGrav have cleverly concocted an imaginary interferometer that stretches for thousands of light years, and all we need to use it are the good old radio telescopes that we've been using for decades. But our calculations will only be as good as our observations. When choosing pulsars to observe, we need to make sure that they are suitable for the task. The best candidates are handpicked and added to a group called a pulsar timing array. For NANOGrav, they have made use of 68 pulsars, which were chosen for the following special properties. They had to be spread all across the sky, so we can figure out how these massive gravitational waves are affecting space-time in all directions. Also, they had to be millisecond pulsars, which means they complete millions of rotations per second. In our recent pulsar video, we talked about how these fast spinning pulsars are expected to be the most stable and dependable when it comes to the regularity of their pulses. In fact, their stability even rivals that of some atomic clocks. We could not ask for better timekeepers to be dotted across space and time. This regularity means that we can take measurements of the time their pulses arrive and continue taking these measurements over multiple years to see if there are any changes happening. Of course, the times of arrival can vary due to all sorts of factors, such as the change in distance between the Earth and the pulsar, as both objects continue moving around space, but we can take this into account quite easily. However, there are less predictable factors, such as random fluctuations in the interstellar gas the light is traveling through, causing delays that aren't coming from the stretching of space-time. How do we get rid of the random noise in our data from pulsars located thousands of light years away? With statistics, we can isolate the gravitational wave background from the random noise by considering correlations between pairs of pulsars in the pulsar timing array. Just like LIGO, one tunnel isn't sufficient. We need 2 pulsars on each end of our imaginary tunnels. If similar fluctuations show up with 2 pulsars, it is unlikely that the random noise aligned in such a way to make it appear, by chance, that they are acting in unison. It is far more likely that there is a common cause underlying both those fluctuations, such as the possibility that the photons from the 2 pulsars are riding the same gravitational wave that are washing by them both. We can then relate these correlations of pulsar pairs with the angular distance in the sky. If there is no gravitational wave background, we expect there to be no correlation, and the graph to show a straight line at 0. However, if the data shows a special curve called a Hellings and Downs curve, that would indicate that a gravitational wave background is responsible for the variances. That's what NANOGrav have succeeded in doing. On the 28th of June 2023, based on over 15 years of continuous observations of their 68 pulsars, they announced strong evidence for the gravitational wave background. This is the graph we've been waiting for. This is a hallmark of gravitational waves, which stretch along one direction and squish in the perpendicular direction. This is exactly what we are seeing with this graph. When pulsars are separated at right angles, their photons are experiencing an opposing effect as they travel to Earth. The error bars in the data appear quite large, but the researchers have calculated that the data shows that the existence of a gravitational wave background is statistically significant at the 3 sigma level. This means that there's only a 1 in 1,000 chance that this is a false alarm and that this data was the result of mere chance. In physics, the 5 sigma level is considered the gold standard for a discovery, but 3 sigma is still very strong evidence. As they collect and analyze more data, astronomers will be able to reduce those error bars and finally announce an official discovery. So, what secrets does this gravitational wave background reveal? While we cannot pick apart the sources of the collective noise just yet, we hope that these techniques will eventually allow us to listen in to specific supermassive black hole binaries and figure out what the signal can tell us about the creation of the universe. Until then, astronomers will continue to use their galaxy size detector to calculate how we are bobbing up and down in the turbulent sea of spacetime. Have you heard about NANOGrav before? What secrets do you think gravitational waves could reveal? Let us know in the comments below. On the 14th of September 2015, scientists at the Laser Interferometer Gravitational Wave Observatory detected gravitational waves directly for the first time, a stunning achievement that led to the 2017 Nobel Prize in Physics. Why was this significant? Well, here's an analogy. Let's imagine that human beings evolved without the ability to see light. For thousands of years, we'd fumble in the dark, relying on our other senses until, one day, someone invented a machine that could perceive light for us. In time, we'd see everything from the tips of our noses to the farthest flung galaxies. This analogy captures the magnificence of LIGO. It's about much more than proving a scientific prediction. LIGO enables us to perceive the physical universe and understand reality on a new level. Like photons, gravitational waves travel at the speed of light as they ripple across space-time. Their signals are all around us. By listening for gravitational waves with some of the most sensitive instruments ever built, scientists are recording tremors of distant, violent events. The formation of black holes, supernova explosions, and, potentially, exotic phenomena we haven't discovered yet. So, what are gravitational waves? What causes them? And why is LIGO's ability to detect them already transforming our understanding of the universe? I'm Alex McColgan and you're watching Astrum. Join me today as we learn about gravitational waves, unpack the groundbreaking technology behind LIGO, and anticipate some of the stunning developments that lie around the corner. Gravitational waves are one of the stranger implications of Albert Einstein's general theory of relativity. As we've covered previously, spacetime is a model that combines the 3 dimensions of space and the 4th dimension of time into a single manifold. All objects with mass create curvature in spacetime, and objects with a lot of mass create a lot of curvature, which we experience as gravity. A simple way to visualize this is to think of a pool ball resting on an elastic surface and a bowling ball resting on that same surface. The more massive bowling ball will create more curvature. As objects move across spacetime, that curvature changes position with them. One of the amazing consequences is that when objects of a certain mass accelerate, they can send ripples across spacetime as gravitational energy. While this requires a special set of conditions, namely a very massive object undergoing acceleration, such a cataclysmic event would send ripples or gravitational waves outward at the speed of light. Think of them like ripples on a pond, but instead of water, they travel through the fabric of spacetime in all directions. As in the pond analogy, these disturbances become weaker as they radiate outward. To an observer, the distance between objects would appear to expand and shrink as the gravitational wave passes. Mind-boggling to imagine. Yet, although Einstein predicted the existence of gravitational waves, he was pessimistic about our chances of ever detecting them. He thought that these disturbances would be so small as to escape our ability to measure them. And who could blame him? Many of the changes in distance that LIGO seeks to measure are 1/10,000th the length of a proton. Yes, you heard that correctly. 10,000 times smaller than a single proton. And yet, these signals would come encoded with all kinds of information about their origins, when they originated, how far they traveled, and what kind of event produced them. This is where LIGO comes in. It consists of 2 observatories funded by the United States National Science Foundation and operated by MIT and Caltech. Among its driving forces are renowned physicists Kip Thorne, Rainer Weiss, and Barry Barish, all of whom shared the 2017 Nobel Prize for their decisive contributions to the detection of gravitational waves. LIGO is essentially a large-scale and very sensitive interferometer, an invention that's been around since the 1880s. An interferometer essentially measures what happens when light waves are combined from 2 or more sources. For example, you could use an interferometer to test whether light travels at different speeds through different substances, such as through air or water. Even a subtle difference in speed will produce an interference pattern when the light waves combine, much like what happens when 2 ripples on a pond intersect. If the peak of one ripple hits the valley of a second ripple, they will subtract from each other, producing a flat surface. However, if the peaks line up exactly, it means that the waves are in phase and add to each other. This is essentially what the interferometer measures with light. By seeing how in or out of phase 2 light waves are, an observer can infer the relative speed of the waves. And the larger and more powerful the interferometer, the more sensitive it is. Here's how it works. LIGO has 2 observatories located in Hanford, Washington, and Livingston, Louisiana. Why 2? Well, you need at least 2 detection sites to triangulate where the signals are coming from. Each observatory continuously fires a powerful laser at a beam splitter positioned at a 45-degree angle. The laser beam has to operate at around 750 kilowatts, powerful enough to vaporize you completely if you got in its path. The splitter then splits the laser beam perpendicularly. The light in each arm travels down a 4-kilometer vacuum cavity with a mirror at the end of it. The beams then bounce between this mirror and a recycling mirror at the other end nearly 300 times, increasing the distance from 4 to 1,200 kilometers. Remember what we said, with interferometers, bigger is better. After completing nearly 300 trips, the laser beams combine at the beam splitter and head to a photodiode, which is a light-sensitive semiconductor. If undisturbed, the beams will be in phase, meaning their frequencies will subtract each other and no light will arrive at the photodiode. But if there's a gravitational wave, the distance each beam travels will be slightly different, and they'll be out of phase. The photodiode will pick up a signal indicating the presence of a gravitational wave. Now, this is how it works in a perfect world, but in reality, the interferometer is constantly picking up noise. To minimize this, LIGO uses incredibly smooth 40-kilogram mirrors suspended by silica threads. Any particles in the interferometer's arms are also a problem, which is why LIGO pumps the air from its vacuum chambers to 1/trillionth of atmospheric pressure. But there's another problem. At these minuscule levels, even quantum mechanics are a nuisance because they introduce randomness into photon behavior. LIGO mitigates this with an optical cavity which squeezes the light. This squeezing minimizes the light phase's noise and squeezes it into amplitude noise, which the interferometer doesn't measure. In other words, the quantum randomness will show up more in the height of the waves. Quantum randomness is a fact of life. It can't be eliminated, but it can be shifted. Much as you might move clutter from your bedroom floor to your closet, the chaos isn't gone, just out of sight for the moment. Plus, the goal isn't to eliminate noise completely, but to get the best signal-to-noise ratio possible. That's a pretty good overview of how LIGO works. So, what has it discovered? As I mentioned earlier, LIGO detected its first signal in 2015. Named GW150914, scientists studied the data and learned that it was caused by the merger of two black holes about 1.6 billion light-years away. These black holes, which were 29 and 36 solar masses, became a binary and spiraled around each other until they merged and released a blast in the final 20 milliseconds that was so powerful. Now, get ready for this number because this is what the scientists actually think. It contained 50 times the combined light power of every star in the observable universe. At the risk of sounding crude, that is nuts. I've read this fact many times over, and I still cannot comprehend what it means. Yet, after traveling for 1.6 billion years and finally reaching LIGO, the disturbance was so faint, it moved LIGO's 4-kilometer arm 1,000th of the width of a proton. To visualize this, imagine the distance between us and Proxima Centauri and changing it the width of a human hair. That is the level of precision LIGO was able to detect. If that's not one of the most astonishing feats in human history, I don't know what is. And this was just the first gravitational wave LIGO detected. The second detection occurred 3 months later in December 2015. That signal also came from a black hole merger, which took place 1.4 billion light-years away. Over its initial 3 runs, LIGO recorded more than 80 black hole mergers, and in August 2017, it detected the merger of 2 neutron stars. Named GW170817, this signal was notable for being the first gravitational wave to be corroborated by electromagnetic observations from 70 observatories across the planet. This was a breakthrough not only in gravitational wave detection, but in multi-messenger astronomy. It turns out, LIGO was just warming up during these 3 runs. As of May 2023, LIGO has begun its 4th run with better sensitivity than ever. After its latest round of upgrades, which kept LIGO offline for 3 years, the observatories now have more reflective mirrors, better mirror suspension, and improved light squeezing with lower quantum uncertainty. And this time, LIGO also has the support of Kagura, a new interferometer observatory in Hida, Japan. Kagra is located underground, making it the world's first subterranean gravitational wave observatory and also the first to use cryogenic mirrors. During an engineering run on the 18th of May, LIGO scientists say they already received a signal that was possibly caused by a neutron star being swallowed by a black hole. We'll have to wait a while for confirmation, but if these early results are any indication, LIGO is about to blow the doors off our understanding of gravitational wave generating phenomena. So, what other developments lie ahead? India is preparing a collaborative project called LIGO India, or Indigo, which will help LIGO triangulate better location data. In 2027 to 2028, LIGO will implement its LIGO Voyager upgrade, which will achieve higher sensitivity with 4 times heavier mirrors and higher frequency lasers. And in the more distant future, a 3rd generation facility has been proposed called Cosmic Explorer. This facility would feature 2 new observatories with arms spanning 40 kilometers and 20 kilometers respectively. Remember, with interferometers, bigger is better. But the proposal that really excites me is the Laser Interferometer Space Antenna, or LISA. This would be the first space-based gravitational wave observatory, which would utilize 3 spacecraft in a 2.5 million kilometer long configuration. This interferometer would be so big and so precise, scientists hope it would be adept at uncovering exotic and theoretical sources of gravitational waves, such as cosmic strings and other speculative phenomena. In theory, it could help us stare directly into the fabric of reality. With a planned launch date of 2037, we're still over a decade away, but it's never too early to start counting the years. So, there you have it. An overview of LIGO and how scientists are using gravitational waves to better understand the universe. They give us evidence of extremely remote and ancient phenomena that cannot be measured by other means, and they can be a secondary way to measure observations made by other instruments like the Webb telescope or Hubble. In time, this revolutionary field should allow us to understand the nature of our universe, its history, and even its future. I hope you found this episode as fascinating as I have. This video by Dan Burns explains gravity in a visual way that's really elegant. What do you think is going to happen to the balls when the teacher drops them? As soon as he lets them go, they start orbiting around the heavy object that is pressing down on the 2D plane. This 2D plane represents spacetime, and the heavy object symbolizes a massive object warping spacetime, or in basic terms, it creates gravity. This mimics gravity in our solar system really well. You can imagine these balls as objects or planets orbiting our sun. Although the difference in the solar system is that there is no friction in space. They don't lose energy, so they keep orbiting. While this is a simulation of 2D space, with objects circling at the edges moving in towards the center, in 3D space, objects move in towards the center from all directions, above and below, as well as the sides. But why do objects in our solar system only orbit in one direction? Check out the pinned comment for more. Gravity can pack a bit of a punch. But did you know gravity is not tied directly to the size of the planet causing it? Take a look at this simulation of a weight falling on a car on different planets and moons to see what I mean. Smaller celestial bodies like the moon or Pluto have less gravity than Earth, causing the same mass to bounce off this simulation car with much less damage. Gravity on the moon is 1/6 as powerful as on Earth, and gravity on Pluto is only 1/15 as powerful. However, it's not a planet's size that really matters, but its density. Although Uranus has a radius 4 times larger than Earth's, its gravity is only 90% of ours. This is because the gas that makes it up is not very dense, making this impact comparable. The same is even more true of Saturn, with 9 times our radius, but 1.08 times our gravity. With enough mass, even low density is overcome. Jupiter's gravity is 2.4 times that of Earth's, and as for the gravity of the Sun, at 27.9 times, it's no joke. The results of this simple experiment may surprise you. We have here 2 different ramps that the metal ball can roll down. The one on the right is smooth and uniform, while the one on the left is bumpy, with dips and rises. In a moment, Professor Kelly will roll 2 balls down each ramp at the same time. What do you think will happen? Both balls are the same weight, and there are no tricks involved, such as magnets. This is pure physics in action. If you're like me, you might expect both balls to reach the bottom at the same time, but this doesn't occur. The professor uses a pencil to drop both balls at once. And there you have it. Although both balls went the same distance down, the dips provided the left ball with a greater chance to accelerate without friction putting the brakes on. This gave the ball enough momentum to speed ahead of the ball on its right, even when it hit the bumps on its journey. When it comes to speed, momentum is a powerful thing. You may have noticed this video didn't have any sponsors, and that's because it was brought to you by our astronauts on Patreon. Consider joining our Patreon to keep these videos thriving, even when they're sponsor-free. It's the reason we can research deep into the topics we love, without cutting corners or chasing clicks. Every new astronaut allows us to explore bigger ideas, and make every upload even better than the last. So if you've ever thought about being a bigger part of this channel, join the crew to power Astrum and keep space curiosity alive.